All right, Chapter 5, Dynamic Routing. This should be a very short video because this chapter is somewhat of an overview of what we'll be talking about in the following chapters in EIGRP and OSPF. So let's go ahead. We're going to talk about dynamic routing protocols in general, distance vector versus link state, and that's about it. So we're not going to get into too many of the specifics. I know the chapter reading does a little bit, but it's going to be kind of redundant in that you'll see this material here and you'll see it in the more specific EIGRP and OSPF chapters. So purpose of routing protocols or types of routing protocols. We've done static routes, right? If we do static routes for everything, we're going to be creating a ton of work and headaches for ourselves. So that's why we have dynamic routing. The dynamic routing protocols can discover remote networks, maintain up-to-date routing information, choose the best path between our two destinations, ability to adjust and to find a best path if the current path is no longer available. And that's done in different ways in different protocols. We've got link state, we've got distance vector, and then we'll get into path vector in CCNA 4, which is BGP. So we talk about that a little bit later on. Okay, so distance vector routing protocols. The only one that's really a true, I would say, distance vector routing protocol is RIP. You will see EIGRP referred to in, for the purposes of this course, it's referred to as a distance vector routing protocol. But you may see it other places referred to as a link state, even a path vector. So EIGRP is a little strange. Again, for the purposes of this course, we're going to call EIGRP a distance vector routing protocol. Okay, that's what Cisco calls it. All right. Routers send and receive routing messages on its interfaces. So they're exchanging routing messages on the interfaces, which is common to most protocols. Share routing messages and other information with other routers that are using the same protocol. Very important. Got to have the same protocol set up. As far as RIP, EIGRP, OSPF, things of that nature. Okay. Even though OSPF is not a distance vector protocol. Routers exchange information to learn about remote networks. R2 might tell R1, hey, I know about this 10.3 network. This is how you get there. R2 will tell R1 about 10.4 because, hey, I learned about 10.4 from R3. So they're all exchanging information that way. Router detects the change in topology change and can advertise this change to other routers. So in both, if I'm remembering this correctly, in both EIGRP and OSPF, what the routers can send out is an update when they see a change to the topology. And if that update is something that another router doesn't have, then the other router is going to request the full update to the path that is changed. So then a little bit of an exchange goes on here. Again, we'll talk about that exchange and what exact packets are involved in that in the following chapters on specifically EIGRP and OSPF. Okay. Describe the process to achieve convergence and build a routing table using the graphics above. Well, basically the routers are all going to exchange information, and once all of their information has been exchanged and R1 knows how to get to all of the networks here, R3 knows how to get to all of the networks there, and of course R2, then you've converged. Once all the routers have exchanged information, they have a full routing table, they know how to get to all those networks. Convergence has been achieved. Which networks are directly connected? Well, what's directly connected? 10.2 and 10.3 for R2. For R1, 10.1 and 10.2. So that's pretty self-explanatory. What is one hop and what is two hops away? So for R1, from its point of view, one hop away would be 10.3 because you had a hop one router to get there. 2 hops away, 1 router, 2 routers to get to 10.4. Going back the other way, you can see 1 hop for R3 to get to the 2 network, 2 hops for R3 to get to the 1 network. So you've got that there. All right, some more information on distant vectors, neighbors. Our routers that share a link are configured to use the same routing protocol. So if you're using the same routing protocol, the router's right next to another device, then they are neighbors. Okay. You can have routing protocol neighbors and then just Cisco neighbors. Cisco neighbors would be both routers and switches, CDP neighbors. And then if you're seeing your like EIGRP neighbors or OSPF neighbors, then you're only going to see routers. So there is a difference a little bit there, and depending on which command you use. The router is only aware of the network addresses of its own interfaces and the remote network addresses it can reach through its neighbors. Okay, so the router only knows which direction it has to send traffic to get to a certain network. It doesn't know exactly each link that its data is going to go through to get to a certain network. It just knows the cost it's going to take to get there and which direction it's sending it out, which is different from your link state protocols. In the link state, they basically know everything. So it's a bit different. Okay. Not aware of the network topology. That's what I just said. That the router is not aware of the entire network topology in distance vector. Okay, it only knows what paths it needs to take to get to certain destinations. Only concerned about itself. Distance vector, very selfish. The router doesn't care about the other links, just needs to know what it needs to do, how and which direction it needs to go, and that's good enough for it. Some distance vector routing protocols send periodic updates, like RIP will send periodic updates. That does kind of cause a little bit more congestion on your network, but that's just the way that the protocol works. EIGRP will send updates when there's a change in topology. Otherwise, you're just sending hello packets to make sure your neighbors know you're alive. Okay. Distance vector algorithm. Sending and receiving, routing information. We'll talk about how it calculates the best path in EIGRP versus RIP. A little later, EIGRP has a couple factors that can be involved, but only 2 that are involved by default. Detecting and reacting to topology changes, so as links go up and go down, that distance vector algorithm can adjust your paths to accommodate for downlinks changes in the topology. All right, and what's the difference between the V1 and the second version of both RIP and EIGRP? Basically the same things: variable length subnet masking, CIDR notation, supports summarization. We talked about summarization in CCNA 2 very briefly. We'll talk about it more when we get into EIGRP and OSPF and the benefits and downsides of using summarization. It supports authentication of those packets that are being sent. So those are the differences. Same for RIP, V1, V2, IGRP, and EIGRP. Moving right along. Link state dynamic routing. The one we concentrate on is OSPF. We'll be talking about that in chapter something, I can't remember. So shortest path, OSPF and ISIS. Shortest path, first protocols, OSPF, the one we'll be configuring in here. I don't even think we touch IS. We don't touch ISIS and CCNA. Dijkstra's algorithm, basically each link has a cost. Okay, we are trying to find the lowest cost, shortest path. Lower is better, for sure. So for instance, just go through this real quickly. If R4 is trying to send traffic to the network that's over here behind R2, for instance, you've got a cost of 10, and that 22 over here, you've got a cost of 20 plus the 242 over there. You're going to take this path. Okay, so you're adding up the cost, choosing the lowest cost, and that's the direction you're going to go. All right. We'll talk about this a little bit in a second, in the next slide, I believe, but each router is going to be aware of all of the costs here in the topology. Okay. Unlike distance vector, where R4 is just concerned with, oh, how do I get here? How do I get there? That's all I need to know. Okay. If it has no need to know how R5 gets anywhere, has no need to know how R1 gets anywhere. All right. Only concerned about itself in distance vector. In link state, it knows everything, the cost for everything on the network. All right. So there's that. All right, link state routing protocols. Each router learns its own links and directly connected networks. Okay, it's going to learn its own links and directly connecting networks and discover its neighbors through hello packets. Okay, it's going to build a link state packet for each one of its directly connected links with a cost. So if each router is doing that, assigning a cost to each one of its directly connected links, if those are all shared, then each router knows the cost of each link in the topology. And that's exactly what happens. Each router builds that link state packet, then floods it out to all of its neighbors. Okay. They receive those packets, they build a database, they use that database to construct a map of the topology and compute a best path to each destination network. So that's what's going to happen. You'll see a bit more of that if you look in the readings on that section. And then a shortest path first tree is going to be created using that information. How do you get from one router or one network to another, shortest way possible? Each router is going to construct that tree on its own, but they should all be identical because they all have the same links and costs in their topology, that map they made of the entire network. Okay, so if that is the case, which it should be, all of those routes should be the same. Those paths are added to the routing table. All right, so it takes those links, takes those costs, and constructs a shortest path first tree with all the shortest paths from one network to another. Okay. So our advantage is builds a complete topological map of the network, knows about everything. Okay, so each router knows everything. All right, instead of just being concerned about itself. All right, it floods the link state packet immediately to achieve faster convergence. Only sends out a link state packet with new information if there is a change in topology. In contrast to RIP, which sends out updates all the time. This one, OSPF, is only going to send it out when there's a change to the topology. Uses the concept of areas and allows for summarization. Areas allow for smaller link state databases. So you can break up the network a little bit so your router doesn't need to be break up the topology a little bit so your router doesn't need to be concerned with so many links. If you have routers in an area, then they're only going to be concerned with the links in that one area. You can kind of break up those areas, and you'll see that when we get to the OSPF chapter. It basically allows for faster convergence and is less taxing on your routers because it doesn't need to know about as many link states. Okay. Disadvantages: requires additional memory to maintain the database and shortest path first tree. Requires more CPU processing power to calculate the shortest path first algorithm and create the map of the topology. And requires more bandwidth during initial startups of the router and could cause an issue on unstable networks with all that flooding of link state packets, but you're probably fine if you have a modern network to set that up. So that's how it goes, and that's basically the end of the chapter. Believe it or not, it is. So that's it. That's a short overview of dynamic routing protocols, leading us into which, if my memory serves me correct, is the EIGRP chapter that is next, OSPF after that, and then we're kind of getting done with CCNA 3. There are multiple chapters, though, on EIGRP and OSPF, so it's not like they're short topics. They're the main meat of this course. So we'll get back with CCNA 3 and EIGRP next week.